Okay, I think it's time to start. Hope I'm loud enough. I mean, this micro is only for the video, as I was told, and I hope I'm loud enough for the room. If not, please tell me. Okay, I'm Wolfgang Brocks, and my subject is on computational fracture mechanics. That means I shall talk how to apply numerical methods, particularly finite element methods, in fracture mechanics. And this can be done with classical fracture mechanics, covering calculation of things like stress intensity factors, J integral, or so. Or you can apply modern concepts of cohesive models or damage mechanics in that one. I will not talk about damage mechanics because I think in the time of 4 hours, this will be too much. Damage mechanics alone, I think I could talk about for 4 hours. So after this general part one of concepts, I will talk about calculation, reliable calculation of things like stress intensity factors, J integral. So, because the problem with numerics is the modern programs are so nice, they always calculate something. And you can calculate pretty big garbage with it. And it actually happens. What people, even in scientific contributions, which they submit, call the J integral, and they have no idea at all what they are calculating. So my intention will be just to give you some feeling what you actually do if you're calculating something. Okay, I mean, André already talked about these concepts in linear elastic fracture mechanics, LEFM, and small-scale yielding, and elastic plastic fracture mechanics. Well, nevertheless, I shall repeat a few things. Repetition is good for learning, and second, it's important for making clear what my nomenclature is, what I call what, and give you the ideas with respect to the next part of calculating all those. Here. Okay. Well, yes. Fracture mechanics always starts with saying that there are 3 modes of opening of a crack with the 3 deformations. A mode 1, and usually if you're reading about fracture mechanics, you have a mode 1. I think 90% of publications is on mode 1. Nevertheless, mode 2, which is in plane shear, and mode 3, which is out of plane shear for torsion mainly, are also important or can be important, as you will see later. I have an example of that one. And this is number 1, the 3 modes. And number 2 is generally in fracture mechanics, classical fracture mechanics, you have 2 kinds of approaches. One is the stress intensity, that you're calculating quantities which dominate the stress distribution and strain distribution at the crack tip, in the near field of the crack tip, which is K in elasticity and J in elastoplastic fracture mechanics. And alternatively, there's the energy approach, which was introduced by Griffith. And you calculate energy release rate by that, and there is a relation between the two, as André has shown you already, between K concept and G, energy release rate. And J integral actually is in elastoplastic something one which makes both, which is an energy release rate, which also dominates the crack field at the crack tip. So yeah, so this is in elastic fracture mechanics, LEFM, the Irwin equation, that the stresses ahead of the crack tip, it's described in a polar coordinate system with a distance r and an angle theta here, is Well, the product of a function of r and a function of theta. And these functions of theta depend on the mode. The function of r, which is 1 over square root r, is actually the same for all modes of fracture and for all geometries. So that's the interesting thing. You have a 1 over square root r for the stresses and also for the strain then. And, well, if you read this original article by Irwin, you'll find out that he already talks about there is a singular part and there is a constant part, which you later on call the T-stress. You see, this was in 57, and it was reinvented or refound, redetected again by Rice to explain certain effects of constraint. Ahead of the crack tip, the plastic zone is affected by this so-called T-stress, the non-singular term, but it can be also found in Irwin's already, and it's actually based on the series expansion of Williams of the stress field. Anyway, so what I will talk about later is how to calculate these stress intensity factors. In finite element programs like Abacus, you can have also the possibility to calculate T-stress. I will not go into details on that one, but just mention this is a not very new concept, but it's still in that one. Okay, and now your K factor, your stress intensity factor here for mode 1, this is a mode 1 situation, can always be written as remote stress, far field stress, which I called sigma sub infinity, times the square root of crack length A. And this 2 pi actually, yeah, well, you have it here and you have it here, so they will cancel out anyway. But they have been introduced like this one. But it's important. You have this remote stress. You have a square root of the crack length times some factor, geometry factor of some factor of the geometry. Okay, and this is a general asymptotic solution, which is the sum of all the 3 modes, always the same, K1, K2, K3, with angular functions of theta for mode 1, 2, and 3. And whereas stresses have a 1 over square root r singularity, the displacements are not singular, they are square root r. Okay. Now the angular functions, they are cosines and sines of several things. They can be described analytically. This is how they look like. You see, this is for xx, and this is the red one is for yy. They are symmetric to 0 for plus theta and minus theta. They have to be 0 at the free surfaces, and the shear stresses are skew symmetric. They are 0 in the ligament, and of course they also have to be 0 here and there. So this is for mode 1, and this is for mode 2, which is different. This is the in-plane shear, that xx is skew symmetric, yy is skew symmetric, and now shear stresses are symmetric here, which is the green one here, symmetric to theta equals 0, which is a ligament. Okay, this was a stress intensity approach, where the crack tip field is characterized by factors k for the 3 modes. And you have a singular distribution of stresses and strains, which is not physical. It's a mathematical solution because you have a sharp crack tip of 0 root of single 0 radius of the crack tip. Now, Griffiths had an alternate approach looking at the energy which is stored. Sorry, I always mix this one. He was considering an large plate, an infinite plate, with a small crack inside under biaxial loading. And he came up with the criterion that a crack will extend if the derivative of the elastic energy stored in that one over the crack phase, the change of the crack phase, minus some quantity which is a material one, which is the separation energy, and the derivative of this separation energy over dA crack is greater than 0. That means that this is larger than that one. That the energy which is released is larger than the energy, than some kind of material constant, which is the separation energy over dA crack. Now, the energy release rate, like this one, is then the derivative of that quantity, and this minus this one you call, because if the crack extends, the energy decreases, so this part is actually negative, and the negative of this one is then the energy release rate, which is called G elastic, and I call this the work of separation, which is an energy per area, which is a derivative of some material quantity, U separation energy over dA crack, and it's usually called 2 gamma, because you have an upper and a lower surface, which somehow is the energy which is needed to create new surfaces. And I also call this gamma C, and I will use this later on in the cohesive model, because this is actually what is modeled also in a cohesive zone model. Okay, and Irwin, again in 1957, in his paper, found out that this energy release rate, G elastic, is K squared over E prime. E prime is different from plane strain and plane stress. In plane stress, it's just the Young's modulus. In plane strain, it's Young's modulus over 1 minus nu squared for a mode 1 crack. And for a mixed mode crack, with all 3 modes, it's like this one. It's 1 over E prime K1 squared plus K2 squared plus 1 over twice the shear modulus K3 squared. Okay, that means if you have the 3 stress intensity factors, you can always calculate the energy release rate here. The other way around, it's a bit difficult if you want to get 3 numbers out of 1. I'll come to that later, how this is done. Okay, well, yes, for the Griffiths crack, it's important to know, because sometimes this is missing, that this dA crack, the extension of the crack for a configuration with, like this one, with 2 crack tips, you have to do this one, whereas for single-edged specimens, like a CT specimen or a single-edged tension specimen, it's just D over thickness times dA. But in this case, for a center crack panel, you have to take care that this is twice the dA crack, this one. Okay, now, next one, just to introduce a thing like a J integral, or also the same goes with C star in creep. Generally, some path-independent integrals have been found and defined independent of fracture mechanics, just from physics and theory of elasticity, or generally in physics. So I'll give the general concept of path-independent integrals here. Assume that phi of x is the coordinate, is a field quantity. Field quantity means it's dependent on x. It may be scalar function, it may be a vector function, a tensor function, whatever, which is steadily differentiable with respect to x in a domain B, and which is divergence free. That means d phi over dxi is 0 within B. Then from Gauss' theorem, you can convert this quantity, the integral over the domain B, in an integral over the surface of the contour, the outer surface of B, dB here. F times NE, which is the outer normal, and this is the surface element, and this is the volume element here. Now, if there is some kind of singularity in that field, which is that red point here, this S here, then of course this does not apply. This singularity can be, for instance, in fluid dynamics, it's a well, for instance, or a sink. In fracture mechanics, it's a crack tip, or it can be a dislocation, or whatever. Any kind of point where this is not defined, where the derivative is not clearly defined and uniquely defined, and where you have some kind of quantity becoming infinite. Well, what you're doing is you exclude it. If this is your domain here, then you exclude the singularity by going around like this. Okay, back to that one. Now, sorry. Now, in this green one now, again, Gauss' theorem will hold, because the singularity is excluded, and therefore this is divergence-free. Now, then your integral over the whole area consists of, well, the integral over dB, which is this one, plus this one, plus this one, plus this one. And this is 0 again, because it's divergence-free. Now, well, it's easy to see that this integral dB minus and dB plus cancel out. This is a negative of this one. And, well, this integral here, where the contour is clockwise, is minus the integral anti-clockwise, which is written here. I'm afraid there is a typing error in your, where this one is supposed to be a clockwise integral like this one. And I think this is different here in your, so you please correct that.
It's okay. It's okay.
Is it?
Yeah.
Okay, then maybe it was a misprint in my one. Anyway, okay, so, but this is, and if you introduce this one, you come up that the integral in the same anti-clockwise around this contour is the same as this one, and this is the equation of path independence. That means whenever you have a contour of this quantity phi times n, the outer normal ds, it does not depend which contour you take, if you just exclude the singularity. On the other hand, well, let's go on. If there is no singularity in the whole domain, this will be 0. But in this one, it's actually calculated to characterize a singularity. Now, in 1965, Eshelby formulated a conservation law for the so-called energy momentum tensor. The energy momentum tensor is this one. Pij, which is the strain energy density times one tensor, or the Kronecker symbol, minus the derivative of strain energy with respect to the gradient of the displacement field times that one. And the divergence of this quantity is also 0. And if you now calculate this quantity, that means a contour over some domain, some contour gamma of this quantity Pij times Nj, which is the outer normal ds, you come out with something like a force. That's what people are calling nowadays material forces, which have become very popular. Recently, people doing very old things, just giving them a new name. Anyway, I mean, this is a nice general concept, of course, and for certain applications, I think it's valuable to use this, but for just, well, filling old things into new words. I think it's a bit funny. Anyway, now the J vector is such kind of a material force. The boundary value problem, which you solve for a quasi-static deformation of a solid body B, consists of equilibrium. So this is the divergence of the stress tensor in B. Note that there are no acceleration forces. So this is for static problems, and there are no body forces here. That means no gravity forces here. Otherwise, they would affect this equation. So this is the assumption that you have simply the divergence of the stress tensor is 0. You have boundary conditions with respect to tractions and displacements. That's important. You have small strains, linear strain in B, and now the most important of all, you assume to have an hyperelastic material. Hyperelastic means that there is a strain energy density, which, if derived with respect to strain, give you the stresses within B. So this is, well, actually, in mechanics, it's called hyperelastic. It's some kind of nonlinear elastic material. It's not plastic, but it may be used as an approximation for plasticity under certain conditions. But it's important that whenever path dependence of C of J is addressed, then you have to assume something like this one exists. And if it doesn't, or if the assumption is violated too much, then path independence will not exist anymore. Okay, now the components of the material force, like this one, you see this is the energy momentum tensor again, sigma jk and k uj duj over dxi ds are forces, Fi, 3 components. This is a vector. If this domain B contains a singularity. If it doesn't contain, it's simply 0. Okay, and if you now apply this to a panel of a constant thickness h, then, so ds is h ds, then you obtain a vector j sub I, like this one, which consists of 3 components. It's a so-called j vector. So j is just not one quantity. In general, it's 3 components of the vector. And, well, that's what you do. This is n, the normal. ds is some increment of this contour, and it's an arbitrary anti-clockwise contour around the crack tip, which is now interpreted as a material force per thickness h. And the first component of this j vector is J integral, which has been introduced by Rice in 1968, and a year before by Cherepanov in 1967. Andre, is he still here? I'm not agree with your saying that this was done in 75. This is in 67 already. Anyway, but they didn't know of each other before. So one published in Russia and the other in the US, and at the time it was difficult. So this is the first component, like this one. And for the condition that you have hyperelastic material, it's a path-independent quantity. It can be calculated in the far field, and it controls, by that, the crack tip near field. That's the interesting feature. And for R going to 0, J has a finite value which is different from 0 only, it's also important, if the strain energy density has a singularity of the order of R, 1 over R, R to the minus 1, which holds for the HRR field, which holds in linear elastic fracture mechanics. For an advancing crack, it doesn't. And therefore, well, the people were very astonished that calculated calculating J integral for a moving crack gave 0 values if you go to the limit of R to 0. And they were accusing other people doing wrong calculations if they came up with 0. But the reason is that for a moving crack, the singularity of the stress and strain field is not of that kind that the strain energy density has a singularity of R over 1. Okay, we'll see later. Now, then later on, Rice showed that this J can also be looked at as an energy release rate. That means as a derivative of U, which is the energy, strain energy, over dA for constant displacement, and minus because this value will be negative. So J equals G. In elasticity, it would be the elastic of Griffiths, but there's also some G in elastoplastic fracture mechanics if you assume plasticity to be governed by a hyperelastic constitutive equation. So in LEFM, you have this one, so that J, or J1, is the sum of the 3 modes of G, energy release rate. As I've shown before, it's this one. And J2, the second component, is this one. This is a product of K1 times K2 over E prime, giving you J2. So with, if you don't have K3, then you would have 2 quantities to calculate for 2 quantities, K1 and K2. So this would rather work, but with some problem, because this is a non-unique equation. It ends up with a 4th order equation which has non-unique values. So you run into problems with that one. So you don't use this in calculating K1, K2 in a finite element program. Anyway, well, yeah, the J integral. There are some hidden further requirement. I mentioned a few. You have to have time-independent processes. It's not included in the equation. That means you cannot use it for dynamics in general. You do not account for volume forces. You have to have a homogeneous material, and in this, what I showed here, no dependence on the 3rd component. That means you have plane fields, plane stress and strain fields somehow, and you have straight and stress-free crack faces, which are parallel to X1. Okay, now there exist extensions to 3D. A few authors who did that. In general, if you're looking at a surface crack like this one, then you defined a plane perpendicular to the crack front, and you have a kind of disk around that one, where you now, have the integral over this contour plus some integral over the faces here, as minus is just on the back side of this one, and the change with the 3rd component is this one. And this gives you an extension to 3D. And there also exist correction terms for body forces, for surface tractions, for thermal loading, and for multi-phase materials. I just give some names to find that. All of this is included in a finite element program like Abacus. So you can just choose the respective option. During my scientific life, I've had at least 3 submissions of papers reinventing the J integral for multi-phase materials again. But this problem has been solved 20 years ago, or more than 20 years ago. So please don't try it again. There exist equations for that one. You see, the problem with this one is sometimes I don't blame the guy who is submitting that. I blame his advisor, who should know. Someone who is starting his science, or who is his or her scientific career, now looks in the internet, and everything which is not in the internet does not exist. But all those publications before 1918 or 60 or something, they are usually not in the internet. So this is something. This is something the advisor should know. Don't forget about that. You're reinventing the wheel. It's also not in the internet, I think. But be careful with things like that. Usually, much more exists than you imagine. Okay. So telling you this is also to making you aware of some literature on problems like this one, extension to 3D, and so on. Okay, this is 3D now. Plastic zone at the crack tips, the small-scale yielding approach. Andre has already introduced that one. So it considers only yielding in the ligament. That means for theta equals 0, and you introduce a perfectly plastic material like that one, and you calculate something which you call radius of the plastic zone, which just means the extension in the ligament. And it comes up with this equation here for plane stress and plane strain. It's generally the K1 squared over the yield strength here, and it's much smaller in plane strain than in plane stress due to this factor here, you see. Okay, and this is one possibility of avoiding the singularity, the unphysical singularity at the crack tip. You just assume for plane stress, so you have a limit here, which is R0, and then you cut off your singularity here, and then you can calculate in order to have equilibrium again that you just have to add another like this one, and then you have a extension of the plastic zone in the ligament, which is twice this RP. And Irwin actually called this the effective crack length. That means he assumes that the crack actually goes to the center of that zone here, and you can calculate an effective stress intensity factors by just assuming that you have an A is not this one, the physical crack length, but the effective one, which is half of the plastic zone plus the physical crack length. And then you recalculate everything, and you dealing with that one, that outside that, you still assume that you have something like a K dominance of the field. This is actually still used in some standards and some codes used in aircraft industry, who calculate, well, R curves dependent on this K affected, without saying this. And I think there exist modern methods, but there are things like that. And the problem with it is that you see, it depends very much if you have plane stress or plane strain, and there are other models like Ductile which give you a third estimate of the plastic zone. And there are factors between. You see, if nu is 1/3, then this is 0.6, and this is 0.44 squared, which is 0.16. That means a factor of 7 or 8 difference from the other one. So it makes a big difference, which is generally physically true, that the plastic zone is much smaller in plane strain or plane stress. But for an assessment, it's very important, well, what did you actually assume to be? Anyway, now the next one is a ductile model, and I'm showing that one because it is one of the origins of the cohesive model. Also, Ductile wanted to avoid the non-physical singularity at the crack tip, and he assumed for thin panels that there is a constant yield strength along some length dp, And if you assume that you're considering the elastic problems for this crack and for that crack, and then you assume that there is no singularity and a superposition of this one, which is with a singular one with some kind of remote stress here, and the other one with this stresses here, which close the crack. The singularity, or the K factor of this one is this one. The summation is supposed to be 0, so that there is no singularity. Then you end up with A over C. C is that one, being this quantity. And then you get an estimate of the plastic zone size like this one, which is A, the original physical crack length times seconds, which is 1 over cosine of this one. This is in stress, remote stress over yield strength. Whenever you see equation with seconds inside, you can be sure it's somehow derived from Ductile, because no one else uses the seconds, which is 1 over cosine, so you have to look at. Anyway, it's important, whereas Irwin has some restriction with respect to the plastic zone size and also has a geometry factor inside over the K factor. There is nothing like this here. The reason is, well, it's a single thing that you have center crack panel, very large center crack panel with a comparably small crack. So this Griffiths crack, so there is no geometry dependence. There's no restriction with respect to the plastic zone size in this equation here. Okay, now one parameter which is used in fracture mechanics is CTOD, and there exist several definitions of that one. One is based on small-scale yielding, Irwin taking the crack opening profile and then calculating the opening, twice the opening at that point of your physical crack with a profile which is calculated using the effective crack. And you see from that one, you come up with your definition of CTOD according to the Irwin model, again, for plane stress, different from this of plane strain. Now, again, you see a difference here. So this is for nu equal 0.3. This is 0.4 times 0.9. So this is about 1/3 difference between the two of CTOD. And also for the ductile model, you can calculate an estimate of delta T using the opening profile of the ductile solution. And this is this equation here. There is no dependence on geometry here. And if you calculate that numerically, you will find out that it's for a Griffiths crack, it's identically to the Irwin one, or at least pretty close to the Irwin plane stress solution here, the numerical values of that. Anyway, so CTOD is something which is used in British standards, and has been used in British standards, whereas in the US they prefer J-integral because it's been invented there. Anyway, but you should get some idea what definition of delta is behind it. In numerics, you have no problems calculating all that. The problem is how to measure it. How can you measure a delta T for a specimen? Anyway, there exist standards for it. But the advantage in numerics is you just can play around and try and look what's it. But if you want to compare this with a material quantity, some kind of resistance for initiation of a crack, then you have to make clear what definition you use in the measurement. Now, Barnblatt model is similar to the idea of Ductile, despite he's not using a constant value of stresses here, namely the yield strength, but some kind of distribution of stresses here, assuming that at that step, of course, they have to be 0. And you call this a process zone, because in that zone, some degradation of the material happens, something in between plasticity and, well, damage which is happening there, so that at the end you have zero stress here. The idea, as before, is to remove the singularity as a crack tip, as unphysical. This was done in the Griffiths approach with the energy. He's not considering the stress distribution. With the Irwin approach of the effective crack length, with the ductile strip yield model, and with the Barenblatt model, which later on became the fundament of the cohesive zone model. So sigma of x, this stress distribution here, is unknown, of course. And you have no possibility to measure it in general. A few cases. Okay, so what was the principal idea of applying a cohesive zone model? Not to use a sigma independence of x, the distance from the crack tip, but using a sigma, a stress traction independence, well, of a fictitious opening here. Sigma of delta. And you call this a traction separation law. You cannot measure this generally either, but you can introduce it into models and look how they work. And then in the end, take this one which works best. So there exist several models. The first one used in '76 and civil engineering by Hillerborg for concrete, just in linearly decreasing stress-strain law, traction separation law, or decohesion law. That means you have a maximum stress here, which is this parameter here, sigma c, and you have a maximum parameter delta c here, where you have no stress carrying capacity anymore, and you just draw a straight line, which is a simple model anyway. Later on, people modified this. There is, by Bazant, for concrete, first use this one by introducing a second point in between here and having this one, which is also used for concrete and which is particularly appropriate for the behavior of concrete structures. But if you take this point from here to here, you can use the same model as a ductile one. But you need, of course, an additional point here. And then in 1987, Needleman has introduced this kind of polynomial law here, third order polynomial, and others. I will talk about later in the second part of my presentation. Anyway, now looking at the energy release rate for small-scale yielding, if you define again this G as minus du over crack extension for constant crack, then you may call this small scale. It's not an elastic anymore, but you have a plastic zone now. And you can call this a G small scale yielding, G small scale yielding. And actually it fits to this one via K1 F effective squared. And this is approximately A plus RP over A. And so you see it consists generally of the elastic one and a plastic part. And for small-scale yielding, this still works. It becomes problematic if this one becomes too large, because then plasticity spoils everything. And it does not only describe what's happening at the crack tip in the end, but it describes what's happening in the far field, the remote specimen. But for small-scale yielding, it works. And you can, again, define a gamma C, which of course, now, due to that plastic, one is greater than the elastic part. And this gamma C now provides you a fracture criterion if this G, small-scale yielding, equals gamma C, then you again will have propagation of the crack, which is a local criterion, which is used in the cohesive model, where you have a gamma C, which is the integral over the attraction separation law here. There's the separation energy, which is now what happens at the crack tip, locally at the crack tip. Different from our curves, which is supposed to describe the global behavior. This is the local one, so this works much better. Now, elastic plastic fracture mechanics. Elastic plastic fracture mechanics is generally a theory based on the so-called deformation theory of plasticity. That's important. It's fracture under large-scale yielding conditions, but it uses a constitutive model which describes hyperelastic materials. That means there exists a strain energy density, so that the derivative of that with respect to strain gives you the stresses. And they call this deformation theory of plasticity. And all the literature on elastic plastic fracture mechanics and analytical solutions use this one. Sometimes saying what they're doing, sometimes not saying. Okay, and this energy density is this, the integral of sigma times delta, and approximately you just consider this nonlinear part or plastic part here. So actually in the following, this E stands for linear elastic, and this P stands for nonlinear. P for plastic, but it's not actually real plasticity. It's some kind of, well, simplified theory of plasticity, or Hanke plasticity. There are finite plasticity of Hanke, which is actually the same. Now, with that one, then, you can calculate things like the energy consisting of an elastic and a plastic or nonlinear part, like this one. And this is used to calculate J from experimental records, because then you can calculate this. This is, of course, the linear elasticity, and this is something you can derive from the load displacement curve. But again, this is based on deformation theory of plasticity or Hanke theory of finite plasticity. It's not really incremental theory, but it worked for a while. It will not work if crack extending, because it becomes less and less appropriate for an approximation of incremental theory. Anyway, now, in addition, most of the equations use also a particular approximation of the stress-strain curve, which is this power law of Bromberg and Osgood, like this one, which is a power law alpha times sigma over sigma naught to the power of n, having thus, besides the normalizing factors sigma sub naught and epsilon sub naught, they have two parameters, alpha and n here. And generalized to 3D, you have this one. And you see for differing n, if n is low, you have a high hardening. If n is high, you have a low hardening. Be careful. There is a similar one where the power is on this side, and you get up with exponents smaller than 1. And with that one, you always have exponents larger than 1. So this other one is 1 over this here, but you have to take care which one you have, whether it's sigma is epsilon to the power of n, or whether epsilon is sigma to the power of n. Actually, this is some kind of nonlinear behavior which has no real plastic yield strength. But it is nonlinear from the beginning. They all go to the same point here, but it's nonlinear from the beginning. Okay, in Hutchinson, Rice, and Rosengren established a solution for the stress and strain field, as that one we've seen in LEFM, which gives you a really nasty fourth-order nonlinear differential equation, which can only be solved numerically. And you just consider the nonlinear part of the whole one, like this one. So sigma is some kind of, well, intensity factor again, r to the power of -1 over n plus 1. Now look, n equal 1, then you have r to the power of -1/2. You have the elastic solution in the limit. And this is the one for the strain here. And this K sigma, the intensity factor in this HRR field, is this one here. It's J over, well, the parameters of the Ramberg-Osgood equation. And this is some kind of numerically calculated integral, very long one, which you can find tabulated. And again, you will see, take n as 1, then you have square root of j here, which is k. So it all comes to a good end. So people were very happy with this one. Everything fitted. It's just some kind of extension, a bit more complicated and nonlinear of linear elastic fracture mechanics to elastic plastic fracture mechanics. And as long as you do not have really crack extension, this works not too bad. But if you compare this one with incremental theory of plasticity, you will find out that J is not path independent anymore. And the question is how to deal with that. And I will talk that. Okay, yeah, what you also see here is that the product of stresses and strain is of the order of r to the -1. You see this one times this one here, which is important that J has a finite value, or strain energy density has a finite value, and therefore J has a finite value. Okay, these are the angular functions which can be calculated numerically. That's not really important for us right now. You can also define now a crack tip opening displacement for EPFM again, and this was some idea of Xi in 1981. It looks rather curious what he did. He intersects the crack opening profile with two tangents under the angle of 90 degrees. The interesting thing, if you define it like this one, you end up in a simple relation between delta tip, crack tip CTOD, crack tip opening displacement, and J, and some parameters here, and yield strength here, or the normalizing stress, which is usually taken as a yield strength in the Ramberg-Osgood one. By the way, you may establish elastic plastic fracture mechanics based on deformation theory without using Ramberg-Osgood. This is an additional ingredient to the theory, but it's separate. You can also do different things. So it's not the same that you always have to use deformation theory with Ramberg-Osgood. Anyway, so these are the functions which can be for the well, this d here, this constant here, independence on the Harden exponent n. Anyway, so this can be calculated, and that's a nice, actually, that's a nice thing again, as before. If K is a fracture parameter, then energy release rate, because they are related to each other, is 1. Then J is a fracture parameter, and CTOD is 1, because you can always calculate one to the other one. And so it's the same here. Now, path dependence of J. I will talk about it a bit later again, but it's important to see. Now, I have an example of a compact specimen here. And in a finite element simulation, plane strain, and a stationary crack, that means not growing crack, applying incremental theory of plasticity, using different contours around the crack tip, and comparing this with a reference value, which is taken from the ASTM standard, which is for experimentally calculating J from load displacement records, which is a far field value because it's from external forces and load line displacement. So the reference value is a far field value. So you have always to keep that in mind. What you need in your numerical calculation to compare with experiment has to be a far field value, which you have to approach. So this is done like this one, splitting it in elastic and a plastic part. This is the elastic one is K1 squared over E, and the plastic part is evaluated from the load displacement curve from the area under the force over plastic load line opening displacement times some eta factor. Anyway, you're making a small strain analysis, and despite this one, I will not call it, this is not correctly calculated. This was a contour touching the outer surface, so this does not work. All the other contours coincide and agree with the reference value. If you believe doing it better, making a large strain analysis, it's counterproductive. You see, your path dependency increases. And you get a lot of different values which come closer and closer to the reference one. And you see after this is the contour number 20, which is that one, you see in the end, there is no big difference anymore. So you have reached the far field values. And you can think, well, this is the correct one. The correct one, which has to be used for comparison with experiments, because it corresponds to the far field value according to that one, calculated from the external forces. I have some criticism against Abacus. It does a good work. It calculates correctly, but don't believe everything that's written in the theory manual. There is some point where it says, well, if you have path dependence, you may consider to do a large strain analysis. Well, that's counterproductive. It becomes worse. Anyway, there are other things like that. Just to show you here what's the difference between having incremental theory of plasticity and deformation theory of plasticity. And you have to deal with path dependency, or you use small strain theory. Anyway, the J integral was derived for small strains. So why use a large strain analysis? The stresses you calculate with that one, you cannot use. It's garbage. But you have to decide. If you want to have an easy J, use a small strain analysis. Want to have more or less correct or reliable stress values, you do a large strain analysis, and then you consider the path dependence here. And always use that one at the end of the line. That means when it starts not changing too much anymore for having larger contours. Okay, now what about stresses at the corrective HRR field? So this again is an analysis with incremental theory of plasticity and a large strain analysis. When you see it's not too bad after all. You have a regime here where large strain dominates with a maximum of stresses ahead of the corrective because the corrective is blunting. So this sigma xx, they have to be 0 due to boundary conditions. Sigma yy, this is the maximum one, and set that the third one is just half of it in between. So it goes through maximum, and then you have some kind of power law here, and here. And what you see, that the normalization with respect to this quantity let all these different calculations coincide. So this, the open symbols are analysis for 250 Newton per millimeter of J, and this one 380 millimeters. They fall on top of each other just due to this normalization here. So it says J somehow dominates, even if it's not the HRR field. It dominates also this one. But in a large strain analysis, which is much more complicated. Anyway, and if you draw a double logarithmic of that one, then you will also find there is something where the dependency is linear, which actually is the HRR dominance field here. This is for the sigma yy, the opening stress is here. And, well, this works here. The third one is not according to the theory of HRR field. But anyway, what is important to see that though incremental theory is something different from deformation theory, the equations which have been derived under the assumption of deformation theory may be a good approximation under certain conditions. as you can see in this case. So this was a compact specimen, a high constraint specimen. Anyway, there's some literature you can use. These are mainly review articles and you see in comprehensive structural integrity, there's something on that one. And sorry. Yeah, no, again, you see, you can find that there. And I think I make a short break, just changing that one, because everybody who fell asleep can now take a coffee or so. I'll continue in a few minutes. So bis wann?